Hey everyone, and welcome back. Today's lesson, we are going to start building the unit circle. So let's hop right into it. Here is a right triangle, as you can see, given that we have our little right angle right over here, our missing angle, angle A, and we're going to call that theta. And just take a second and tell or jot down everything you remember about trig. Now, it should be pretty fresh in our minds since we've been studying it, but give me at least 3 things that you remember about trigonometry. Pause the video if you need a little bit more time, but maybe you're remembering a few things from our past lesson. Maybe you're remembering SOHCAHTOA, right? And so if we were going to talk about this angle measure A right here, we'd have to label this side directly across from it the opposite side. The one across from the 90 degrees is always our hypotenuse, and the one next to is our adjacent side. So we could say sine of theta is equal to the opposite side. That would be, I'm just going to leave it as this since they don't have any measures, over the hypotenuse. We could define cosine or tangent in the same way. Maybe you could have noticed that this was a right triangle. Perhaps you were speculating that maybe it's a 30, 60, 90 or 45, 45, 90. We know that we can use Pythagorean's theorem, a squared plus b squared equals c squared, to find missing side lengths. We can use SOHCAHTOA to find missing sides or the missing angle. If we were going to find the missing angle, we would need the inverse trig functions, like maybe sine inverse or cosine inverse or tangent inverse, inverse tangent, right? There's a variety of things. You could have just listed basic things like we're looking at angle A, the right angle is at angle C, things like that. But all of this information is going to lead into our lesson today. So let's proceed. So today we're going to be talking about trigonometry and the unit circle. And the first thing that we're going to need, since it's considering trig, is we're going to need our SOHCAHTOA, right? It's really important that we define which sine, cosine, and tangent is. And you guys have been really good about remembering how these proportions work, right? It says that sine of the angle, whatever angle we're looking at, is equal to the opposite side divided by the hypotenuse. So it's really that ratio of the opposite side, this side right here, if we're looking at angle A, the opposite side, divided by our hypotenuse right here. Or if we're looking at cosine, that's going to be the adjacent side divided by our hypotenuse over here. Or if we're talking about tangent, that's where we're going to get more of our opposite side again, divided by our adjacent side. And these are all in relation to whatever angle we're looking at. Again, it's just that proportion of side lengths. And as I was saying in the previous slide, this can help us find missing side lengths. It could help us find the missing angle that we're going off with. And something else you could have remembered too is if we have 90 degrees in another angle, we can find the last one by the triangle sum theorem, the interior angle sum theorem, where we know that all of the angles have to add up to 180. So these are definitely going to come in handy. So just to get the juices flowing again, here is a triangle. We've got 4, side length 8, side length 4, radical 3. Go ahead and I want you to define sine of A, cosine A, and tangent of A. Pardon me. Okay. So if we're looking at angle A right here, that means this side across is our opposite side. The one across from 90 degrees is going to be our hypotenuse, and the one next to is our adjacent side. So if we're talking about sine, that's our SO in SOHCAHTOA. Sine is equal to the opposite divided by the hypotenuse. Opposite side length is 4, our hypotenuse is 8, and that can be reduced to 1/2. So sine of angle A is 1/2. Cosine, that's going to be ka of our SOHCAHTOA. That's going to equal the adjacent side divided by the hypotenuse. The adjacent side is 4 radical 3, thanks to our handy-dandy labels. And our hypotenuse is 8. Again, we can simplify 4 over 8 to be 1 radical 3 over 2, or just simply rad 3 over 2 would suffice. And lastly, we have tangent. That's that's the TOA. Oops. Pardon me. TOA. So that means we're going to have opposite side length, which is 4 over our adjacent, 4 radical 3. When we do this, we can simplify 4 over 4 to being just 1 over radical 3, but we have to rationalize our denominator. So we got to multiply rad 3 over 3, and ultimately we end up getting square root of 3 over 3. Now, my last question for y'all is, what do you think the measure of angle A is? And then once we figure that out, what do you think the measure of angle B is? So if we're looking at all of these side lengths, let me highlight them really quick, right? We've got 4, we've got 8, and we've got 4 radical 3. If we look at that, this actually relates to a very specific triangle, right? If we think about the fact that normally the hypotenuse for, like if it was a 45, 45, 90, that triangle looks like x, x, x radical 2. But we don't have that here. We don't have the square root of 2. So it's certainly not going to be that triangle. However, there's another one. We have our 30, 60, 90 triangle. And when we do that, across from the hypotenuse is 2x. Across from the smaller side is just x. And the longer one is x radical 3. So if we think about that, if 4 is equal to x, that means that this has to be the smaller angle, 30 degrees. So angle A has to be 30 degrees. And well, if angle A is 30, angle C is 90, that leaves this angle B to be 60, because 60 plus 30 plus 90 is 180. So we have our special right triangles. This is going to lead us into our unit circle, believe it or not. This is why it's so important to us. So we have our 30, 60, 90 triangle with that proportion. Again, across from the smaller side, x, across from the hypotenuse is always the one that has the number 2. For 30, 60, 90, it's 2x. And across from the longer angle, we have x radical 3. The 1, 2, 3 triangle I've been telling you guys about. And then when we go to our 45, 45, 90 triangle, we've got x, x, and x rad 2. Again, both of these sides right here are congruent because it came, you can see from this diagram right here, it came from a perfect square. And obviously, all of the sides are congruent in a square. So we're going to use this to build our unit circle. So here is like a quote unquote graph of it. Go ahead and pause this video and take a second to let me know, what do you notice about this? List as many things as you can. Then ponder the question, why do you think that this is called a unit circle? And then, excuse me, then list 4 coordinates that you can see directly on this circle. So like I said, go ahead and pause the video, think about these, and we'll be right back. Okay, so some of the things I notice off the top of my head, and you might notice this too, is like obviously it's a circle shape. I see that we have like this radius right here from the center all the way out here has a length of 1, right? Length of 1, length of 1, length of 1. And that kind of relates to like the 4 coordinates we see on the circle. Like if I were going to list this, if this is the x-axis and this is the y-axis, then I would say that this one is 1, 0. The next one is 0, 1. The one over here is negative 1, 0. And this guy down here, x is 0, but y is negative 1. So we kind of like knock that guy off. And I don't know if you can notice anything else. I'm not sure. I don't want to give away too much. So I'm curious to see what you guys noticed about this unit circle. But the question is to like, why is it called a unit circle? Well, like I guess units are are typically, when we're talking about math problems and stuff like that, we have units of measure. And so unit is usually like the standard or whatever we're measuring by. And so since like that radius is equal to 1, that's a pretty simple, straightforward unit to be measuring with, right? So that's actually why it's called the unit circle, because we're going to call one unit, like this distance right here, that length of 1, that's going to be our quote unquote unit. So this circle just has a radius of 1, a diameter of 2. That is what we're going to be looking at as we begin to build this unit circle, which is essential for trigonometry. We're going to refer back to this unit circle time and time and time again. As a matter of fact, you guys are going to start today the process of like recognizing patterns and things, but eventually you will have this memorized because it is going to be so essential as we move in with all 6 trig functions, the reciprocal functions, our inverse functions. It's just going to become so handy for us in our calculations in trigonometry that building this unit circle is really going to be like the foundation for the last part of this unit, the last unit of our class. So here we go. We're going to label each quadrant below with quadrant 1, 2, 3, and 4, and then we're going to state the signs of any coordinate in each quadrant. And so we're just going to start, and I'm going to use Roman numerals to label the quadrants because that's how we typically do it. We'll start with quadrant 1. It's always like this guy over here. This quadrant over here is always considered typically quadrant 1. And if we look at it, if we think about it, right, if we're moving, here's our axis, and this would be like our x direction, right? And then we could have, I don't know, maybe this guy, up and down. That's going to be our y direction. And so when we're determining like what, I should have used a different color. Let me do this over. I'm going to choose blue for our x-axis. And then we'll have green for the y, right? And so when we're looking at quadrant 1, notice that we're starting at 0 and we're going this way. We're going in the positive direction. So that's why the x coordinate is positive. Similarly, if we start at 0 and we go upwards, we are going in the positive direction for y, which is why we have positive, positive. Now, we're going to kind of move in these quadrants in what I would call counterclockwise. So this is going to become quadrant 2. And if we look at it, x is moving in the negative direction, but x is moving negatively, but y is moving positively. So that's why we have negative, positive. Quadrant 3, we're still moving negatively for the x direction. And now we're actually going to point downwards. And down is towards like negative infinity. So this is going to be quadrant 3, negative, negative. And I'm sure lastly you can understand now like where I'm going with this stuff when we move into quadrant 4, which is going to be IV. V represents 5 in Roman numerals, and so the letter I or in front of it means the one before, so 1, 4. 1, 5 means 4. In quadrant 4, we're pointing down in the y direction, but we're pointing to the right. It's a positive direction in quadrant 4. So make sure you have something like this. It can be something as simple off to the side where you have plus, plus, minus, plus, minus, minus, plus, minus. And then you could do 1, 2, 3, 4 if you wish. I will refer to them with Roman numerals pretty much from here on out. Just so it's a little bit easier. It's not confusing with any calculations that we do. So we're going to actually use this a lot. Now, it makes the most sense. This is a blank unit circle. So you guys should have a blank unit circle. The sub should have that for you guys. And we're going to start measuring this circle in degrees. And notice that when we were labeling our quadrants, we kind of like started here and we went around this way. So we're going to do the same thing when we're building this blank unit circle. And since we're already familiar like with degrees, we're going to start with that. So if we're starting again, like right here, right there, our starting position is going to start us off with 0 degrees. That's a really messy 0, but 0 degrees, right? And as we continue, remember I told you guys the fact that we have this straight line here was super important. So how many degrees is one straight line? Well, that's 180 degrees. So we're going to hold on to that, 180 degrees. From 0 to 180, that's my straight line. And if that's 180 degrees, well, what's 180 plus 180? Well, that's going to give us a full rotation of 360 degrees. So we're starting off with just the basics. We've got 0 to start, 180 at our line, and then to finish it off, 360. Now, I'm going to bring you guys back to 0 to 180. If we're starting here at 0, and this, entire rotation is 180, what is the halfway mark between? What is 180 divided by 2? Well, that's going to be halfway between 0 and 180. That's going to be right here. That's going to give us 90 degrees. Perfect. And if that is 90 degrees, right? If we go 90, 180, what's this next one going to be if we're adding increments of 90? Exactly. It's going to be 270 degrees. And then if we continue on, 270, well, with plus 90, perfect. That adds up to 360. So that makes sense. So we went from 0 to 180, a line, cutting it in half and getting increments of 90, kind of like splitting it up into quarters. Now that we've done that, we're going to kind of repeat this process again. But instead, we're going to focus on the first quadrant, okay? So we're going to focus on here, right? We've got 0 and 90. And notice that we have 3 lines in between. We have a line right here. We have a line in the middle, it looks like, and another line right here. So we're going to split those up. And it makes the most sense if this arc length is 0 to 90, that rotation is 0 to 90, then halfway between that is how many? If all the way is 90 degrees, what's halfway between that? Well, 90 divided by 2, that's going to give us 45 degrees. And we can continue in the same way that we did earlier. So from here is 0 to 45. 45 plus 45 gives us 90. Our next one's going to be right here in the middle. What is 90 plus 45 degrees? 90 plus 45 degrees, that goes in the next one. That's going to give us 135 degrees. And if we go 135 plus another 45, well, that gives us 180. Wonderful. What about 180 plus 45 to get us right here at this angle measure? 180 plus 45. That's going to give us 225 degrees. 225 plus 45 degrees, 270. 270 plus 45 degrees, that's going to give us right here. That's going to give us 315 degrees. And if we do 315 plus 45, that's 360. So far, we've filled in a lot of it. We have, let me get rid of these main things right here in the center. We have filled in, 0, 45, 90, 135, 180, 225, 270, 315, and 360 degrees. And now, excuse me, we're going to need to fill in the other ones. And you might be wondering, why did I bring up the triangles in the first place? Like, what is this degrees? I could have done this without it. Well, it comes in handy next. So notice that we just filled in 45 degree angles, right? So that was the 45, 45, 90. Now we're going to use the 30, 60, 90 triangles to fill in the remainder. So if you think about this little section right here, here's our right angle. If you think about this as being 30 degrees, that's where we're going to come up with this angle right here, 30 degrees. Now, if I change up this triangle just slightly, right here, again, there's our 90 degree angle, but 30 doubled, that's going to give us this arc length right here, That's going to give us 60 degrees. So, and then vice versa, the other angle is 30. So we're going to go 0, 30, 45, 60, 90. So you can see that we're really just adding increments of 30. 30 plus 30 is 60. 60 plus 30 is 90. 90 plus 30 is going to give us our next increment, which is 120. 120 plus 30 will give us our next increment, which is 150. 150 plus 30, that's 180. 180 plus 30, that's 210. 210 plus 30 will give us our next one, which is 240. 240 plus 30, 270. And you can see we're filling in this quite quickly. 270 plus 30 is going to give us 300. Right here, 300 plus 30 gives us 330. And 330 plus 30 gives us 360. So ultimately, at the end of the day, we have filled in all of these degrees. We start at 0, 30, 45, 60, 90, 120, 135, 150, 180, 210, 225, 240, 270, 300, 315, 330, and 360 degrees. So I want you guys to conceptualize. Like, I do want you to memorize this, but at the same time, it's not difficult to construct. If you just think about starting with a line, cutting that in half, and then using 30-degree increments as well, you can fill this in. But there's also a couple really cool songs on the internet to help you memorize these things. So I'm going to post a couple links for you guys just to look at. Again, it's your choice. I will make you listen to them when I'm back in the classroom just because it's really helpful. It's one less thing to think about. But they have this wonderful jingle. And I'm going to do my best to sing for you how the unit circle degrees goes. Just because it makes it really easy to like check yourself really quick if you're not sure. So the song goes 0, 30, 45, 60, 90, 120, 135, 150, 180, 210, 225, 240, 270, 300, 315, 330, and then 360 is the end. And now I hope the unit circle's in your mind. Not a great singer, but like, hey, we do what we got to do. So we filled in a third of the unit circle. So far we have degrees. Next thing that we're going to fill in is going to be the coordinates, which sounds super tricky, but it's actually not. I've secretly been preparing you for this entire lesson so far. And actually, when we first started talking about our special right triangles. So they come from our 30, 60, 90 theorem, our 30, 60, 90 triangles. So you'll see right here, we have this first triangle. And if you remember, this guy was 30 degrees. Here was our 90-degree triangle, or I'm sorry, our 90 degrees. And then this little guy over here would have been 60. Now, remember, this is a unit circle. Unit circle meaning that the radius was 0 through 1. So anywhere along here, going all along this circle right here, has to have a radius of 1. So if we're really looking at this pretty closely, this right here is a radius, just as much as this is a radius, just as much as this. So if we have that value, that means that our radius is 1, right? Since we have the unit circle. But in our 30, 60, 90 triangle, it was supposed to equal 2. How can we make 2 into 1? How can we make 2 into 1? Well, in order to change all of these, let's divide all of our ratios by 2, right? So 2 divided by 2, that will give us the 1. What about the square root of 3? We're going to need to divide that by 2. So that means this side length over here, I'm going to use a different color. This side length over here is going to be square root of 3 divided by 2. And this last side over here, that guy was originally 1. And again, we have to do the same thing. We have to divide it by 2 in order to have that same thing. So this side length has 1/2. Now, one more thing that now that we have like our triangle all set up, this is bugging me. Let me fix that. now that we have that, we need to fill in our coordinates, right? And we remember that our coordinates are pretty straightforward, right? Our coordinates are always x comma y. And if we're thinking about this unit circle in respect to the xy axis, right over here, that means x would be right here along this side. And how long was that side length? Oh, well, that was radical 3 over 2. And similarly, if we wanted to find y, the height, the vertical height up and down, that means that we're really looking at this side length right here, 1/2. And so this is how we're going to build our coordinates, just by looking at these special right triangles, which is incredible. Let's move on to the next one. So our first coordinate is going to be radical 3 over 2, comma 1/2. Ooh, I forgot. Okay, so find sine of 30 and cosine of 30. What do you notice about your answers? So pro tip before we move on and get the next part, the next triangle, label your sides opposite, adjacent, hypotenuse, or use a calculator. So if we're going to label again, this is our angle. This is opposite, hypotenuse, adjacent. Remember that our hypotenuse was equal to 1, opposite was 1/2, and our adjacent was radical 3 over 2. If we found sine of 30 degrees, if we were using SOHCAHTOA, right? So opposite, that's 1/2, divided by the hypotenuse. That's just 1/2. Also, if you use your calculator, sine of 30 degrees, if you punch that in your calculator, you'll get 0.5, right? Fantastic. So we know that that checks out from our calculator, just performing it as long as we're in degrees mode, right? Our calculator says that sine of 30 degrees is 0.5, and then we know from our trig proportion, SOHCAHTOA, it's actually 1/2. And if you look at that, right, if we check that out, that is this part right here. Nope, that's not supposed to be green. That is this side length, right? That's this opposite side, the 1/2. So sine was this side length, 1/2. Now, if we're going to find cosine, right, we're going to go ahead and calculate cosine. Cosine, oops, I wanted that to be a different color. If we were going to do cosine of 30 degrees, let's set up our SOHCAHTOA first. CAH, that's radical 3 over 2, divided by 1. Again, square root of 3 over 2. That means that we're looking at the adjacent side. And also, if you plug in cosine of 30 degrees in your calculator to just see what, like, whatever that's going to be, 30 degrees of cosine, that's 0.86, I believe. Wait. Yeah, 0.86, roughly. And if you wanted to, you could actually put in the square root of 3 divided by 2, and it's 0.86 as well. So those check out. So sine of 30 degrees was 1/2, that opposite side in our unit circle. And cosine of 30 degrees ended up being radical 3 over 2. Radical 3 over 2 right here, right? So that's pretty interesting if we're trying to make a connection to our coordinates, right? Because if we remember, our coordinates were radical 3 over 2, 1/2, right? So that means we have radical 3 over 2 and then 1/2. So we can kind of make the relationship, not kind of, we can actually make the relationship that x comma y is going to become 3 over 2. 3 over 2, that was cosine. So cosine comes first, and then 1/2 came second, cosine comma sine. So we're going to associate that. So whenever we're trying to find the coordinates of something, it's the cosine of that angle, and then sine is the y. And that's just because it's directly relating to the x side and the y side. So our triangle is really coming in clutch. Let's move on to the next point, 45 degrees. So we got our 45, 45, 90 triangle. That means this guy would be 45. This guy would be 45. Again, our radius is equal to what? Now, here's where it gets a little trickier. Notice that the hypotenuse is supposed to be the square root of 2. So just like last time, we need to make that hypotenuse equal to 1. So we're going to have to divide all sides by radical 2, right? So if you take square root of 2 and divide it by square root of 2, that's just equal to 1. So that one's easy, right? Here we have this 1, no problem. But what happens when we're going to need to do this guy? Or this guy, it doesn't really matter, right? 1 divided by the square root of 2, we cannot do that. We have to rationalize our denominator. So if we rationalize, we're going to have the square root of 2 on the top and the square root of 2 squared. So we get radical 2 over 2. So both sides are going to be radical 2 over 2. And again, if we're looking at the x, this is the wrong color. The x side, still positive, rad 2 over 2. Looking at the y coordinate, that's radical 2. That side length is radical 2 over 2. Again, we could determine that cosine of 45 degrees is rad 2 over 2. Sine of 45 degrees is rad 2 over 2. We could even plug it in our calculators. And I believe that's 0.707. Let me double check. Excuse me. Yep. 0.707. Lastly, we're going to flip that 30, 60, 90 triangle. It's the same. It's just an alternative perspective. So if we're looking at this last part right here, because remember that this angle measure here, this angle measure here, that is 60 degrees. So if that's 60, this guy's 90, that guy, has to be 30. So across from 30 was 1, across from the hypotenuse was 2, and across from 60 was 3. Again, we have this predicament where, as a matter of fact, our hypotenuse is not 2. Our hypotenuse is 1. We know that for a fact. That it's on a unit circle. The radius is always 1. So we're going to have to divide everything by 2. This guy will become 1. Our side right here is going to become 1/2. Across from 30 is going to become 1/2. And across from the 60 degree angle is going to be radical 3 over 2 if we're putting it on our circle. Of course, as we move along, this is the wrong color, but the x direction was 1/2. The y direction right here, this side length, that's radical 3 over 2. And so now our 60 degree coordinate is 1/2 comma rad 3 over 2. Again, cosine comma sine. Cosine of 60 is 1/2. Cosine of 60, plug it in your calculator, you get 0.5. Sine of 60 degrees is going to give you rad 3 over 2 if you set up SOHCAHTOA, or if you punch it into your calculator. So once we know this first unit, this first quadrant, I'm going to erase everything really quick. Once we know this first quadrant, notice that we can draw similar triangles all across the entire thing. So I'm going to start with this one, right? Here was our 30 degree triangle. And if you think about it, this guy can come all the way over here and draw another 30 degree, right? Similarly, we can go over here and this part right here is going to be 30 degrees. And if we go across this way, that's 30 degrees. So as long as we have, they're all going to be the exact same triangle, right? It's just this one's going to be positive, positive. This one's going to be negative, negative. This one's going to be negative. No, this one's going to be negative, positive. Quadrant 2, quadrant 3 is negative and negative in both directions. Quadrant 4 is going to be positive, negative. So we can take that triangle, those coordinates, remember it was 1/2 root 3 over 2 in your notes, and we can just transform them, change the sign. So if we go over to quadrant number 2, it's going to be negative 1/2 positive root 3 over 2. If we move over this way, we're going to follow this. We're going to take that coordinate 1/2 root 3 over 2 and change it to negative 1/2 root 3 over 2. If we put it into this quadrant right here, quadrant 3, take this coordinate 1/2 root 3 over 2 and make them both negative. So negative 1/2, negative root 3 over 2, right? Moving over to this one, the x coordinate is going to be positive, so we'll have positive 1/2. The y coordinate is negative root 3 over 2. And we can kind of use that to transform all of our triangles, right? This guy right here, our 45, 45, 90, right? There's a really bad drawing, 45 degrees, another 45 degree increment, another 45, and another. Again, these all draw similar triangles. Again, positive, positive. X is positive, Y is positive. In quadrant 2, X is negative, but Y is positive. In quadrant 3, X is negative, but Y is negative. In quadrant 4, X is positive, Y is negative, right? So we can take that coordinate root 2 over 2, root 2 over 2, and just change the signs. The last one we can do is our 60-degree triangles that we just went over, right? The 60-degree increments. Notice that if I drop this side down, again, that's going to be 60 degrees. If I rotate this guy all the way out, this is going to be another 60 degrees to get to that 120-degree mark. And if I drop this guy down, we have all of these similar triangles. So once we know the first quadrant, which was not hard to create, we technically know all of them. So I am going to post this amazing unit circle coordinates song for you guys. I want you to listen to it. It really helps to memorize the coordinates. Again, I want you guys to conceptualize the relationship between the triangles, but the coordinates are super awesome. This song is amazing. It starts, I forgot the unit circle trigonometry. It's super duper catchy. So go ahead, fill in your unit circle, get in that practice. I want you guys to start recognizing patterns. You might notice some once you've filled in your entire unit circle. Peep those, figure out ways to help your brain memorize this unit circle. And I will have a bunch of practice problems for y'all to do as well. So I will see you. Toodly doodly, y'all. Toodly doodly.